Hello viewers, today in this program I will explain you the integration of vector function under the heading vector integral calculus. The integration of vector is as follows. Suppose f t is a vector function f1 plus f2 plus f3 ijk are unit vectors towards x, y and z directions of a single scalar variable t such that it is continuous in some specific interval. If g t is a vector function such that differentiation of g t is equal to f t, then g t is called an integral of f t with respect to t, and we write g t is equal to integration of f t dt. Thus, g t is equal to I integral f1 t dt plus j integral f2 t dt plus k integral f3 t dt plus c, similar to arbitrary constant of integration in elementary calculus. If c is any constant vector that is independent of scalar variable t, we have d over dt g t plus c is equal to d over dt g t, that is equal to f t. Hence, integral of f t dt is equal to g t plus c. Thus, integral f t dt is called an indefinite integration of f t. The definite integral of f t over an interval a b of its variable t is defined as integral f t dt is equal to g t plus c from the limit a to b, that is equal to z at b minus z at a. I will explain the procedure of finding vector integration with the example. Let us suppose the acceleration of the particle which start from rest is given by 6 t I plus 8 t cube j minus 12 t square k at any instant t greater than equal to 0. Find its velocity at any time. The solution of this problem is as follows. Acceleration A is equal to 6 t I plus 8 t cube j minus 12 t square k, then the velocity v is given by integration of acceleration a t dt, that is equal to integration of 6 t I plus 8 t cube j minus 12 t square k dt, that is equal to 3 t square I plus 2 t 4 j minus 4 t cube k plus a constant c. Since the velocity is 0 at t is equal to 0, we have c is equal to 0. Thus, the velocity of the function is given by v t is equal to 3 t square I plus 2 t 4 j minus 4 t cube k. Now, I will explain the line integration in the vector function form. The line integral is natural extension of definite integral. Consider a definite integral from a to b f x dx. In this integral, integrand is f x. It is integrated along x axis from x is equal to a to b. However, in a line integral, the integrand is integrated along a curve, may be a straight line also. Suppose a curve C is defined by a vector function r t is equal to x t I plus y t j plus z t k, where t is some parameter. Between 2 points p 1 is equal to r t and p 2 is equal to r t 2. This figure represents the line integral along a curve C. the line integral of f from p1 to p2 along the curve C is written as integral from p1 to p2 f dot dr or integral over C f dot dr. By the definition, integral over p1 to p2 f dot dr is equal to integral over C f1 dx plus f2 dy plus f3 dz, that is equal to integral from t1 to t2 f1 dx over dt plus f2 dy over dt plus f3 dz over dt whole integrated over t. For example, the integral from p to q f dot dr is equal to integral from p to q 2xy dx plus 3y square dy plus yz dz. Here the limits of integration are from x is equal to 0, y is equal to 0, z is equal to 0 to x is equal to 1, y is equal to 2, z is equal to 3. It becomes the integration after performing the integration and giving the limits, its value becomes 58 units. Now, I will explain you the line integral over closed curve. If C is a simple closed curve, then the integration over the closed curve is written as integral over C in the symbolic form of closed curve f dot dr. The conservative field, a vector field f is called conservative in a region R if for any 2 points p1 and p2 in R, integral over p1 to p2 f dot dr is independent of the path in R joining p1 and p2. Equivalently, a vector field f is conservative in R if for any closed curve C, integration over C f dot dr becomes 0. Here is the picture showing the line integral of a closed curve C. Here the point p1 and p2 are on the curve and the curve C1 and C2 joining the point p1 and p2. Now, I will explain the example for the closed curve. Evaluate the integral over C f dot dr where f is x square I plus x y j and C is the boundary of square in the plane z is equal to 0 and bounded by the line x is equal to 0, y is equal to 0 and y is equal to a. Here the square is on the first quadrant of the xy plane. The solution of this problem is as follows. The integral over C f dot dr is equal to the 4 integral. First integral is along OA, second is along AB, third is along BC and then fourth is CO. Here the integral over C f dot dr becomes the summation of integral OA f dot dr plus integral AB f dot dr plus integral BC f dot dr plus integral CO f dot dr. Here r is xi plus yj. So, dr is equal to dxi plus dyj and f is given as x square I plus xyj. Therefore, f dot dr becomes x square dx plus xy dy. Here the picture shows the path of integration in the form of a square. On OA, the first part y is equal to 0. Therefore, f dot dr becomes x square dx only and the integration of f dot dr along OA becomes integral 0 to a x square dx, that is equal to x cube by 3 from 0 to a, that is a cube by 3. Similarly, the second part of the integral is along AB where x is equal to a, so that dx is equal to 0 and f dot dr becomes a y dy. So, the integral f dot dr along AB becomes integral 0 to a y dy, that is equal to a y square upon 2 from 0 to a, that is equal to y cube by 2. Similarly, on the third part of the integral towards B C, we have y is equal to a, therefore, dy is equal to 0 and the f dot dr becomes x square dx. The integral f dot dr becomes integral 0 to a x square dx, that is x cube upon 3 from 0 to a, that is a cube upon 3. And at the last, the fourth part of the integral towards CO, we have x is equal to a, therefore, dx is equal to 0 and f dot dr becomes 0. Therefore, the fourth integral here along CO is 0. Adding all the four, we find the integral over C f dot dr equal to a cube by 2. Now, I will explain you a well known example of the conservative field. The most well known example of conservative field is the field of gravitational force. According to Newton's law of gravitation, the gravitational force F acting on a mass m due to a mass capital M, which is at a distance r away, obey the equation F is equal to z a small m capital M n upon r square, where z is the gravitational constant and n is equal to x I plus y j plus z k upon under root x square plus y square plus z square is the unit vector pointing from M towards a small m. Now, for any closed curve C, we have integration over C f dot dr is equal to integration over C x I plus y j plus z k dot I dx plus j dy plus k dz upon under root x square plus y square plus z square whole raised to the power 3 here, that is equal to z small m capital M integral over C x dx plus y dy plus z dz over x square plus y square plus z square whole raised to the power 3 by 2. It becomes z small m capital M integral over C dr square upon 2 r square to the power 3 by 2, that is equal to z small m capital M integral over C d over du of 1 upon root of u with negative sign, that is equal to 0, where r square is equal to u. Thus, F forms a conservative field. Now, I will explain you the surface integration of the vector function. Consider two-sided piecewise smooth surface. If it is closed surface, then take outward direction to be positive direction of the surface. However, if it is an open surface, then decide its positive direction by using conventional right hand rule. That is, if we traverse the boundary of the surface clockwise, then our right hand is such a way that the palm faces the surface, then the thumb points in the positive direction of the surface. This way we choose the positive direction of the surface integral. Divide the surface S into number of small surface elements. Now, consider a small surface element delta S around a point r x I plus y j plus z k in vector form on the surface and associate with it a vector delta S, its magnitude being the area delta S and its direction the outward unit normal n cap to the surface at r, so that delta s becomes n ds. Now, if f r is continuous vector point function defined on every point of the surface S, then the limit delta S tend to 0 summation of f r dot ds becomes limit delta S tend to 0 summation of f r dot n cap ds, where the summation is over all the surface elements if the limit exists, called the normal surface S, and is denoted by integral over S f r dot ds is equal to integral over S f r dot n ds, or simplify this integral, we find integral f r dot ds is equal to integral f r dot n ds. Suppose v represents the velocity of the fluid particle at the point r on the total outward flux of v across the surface is given by the integral as v dot ds, that is equal to integral v dot n ds over the surface S. For example, consider a vector field defined by f is equal to x I plus y j plus x to the power 4 k, and suppose we want to find total flux of f across the disk D under the circle x square plus y square less than equal to 9 at the plane z is equal to 1. On the surface x square plus y square less than equal to 9 in the plane z is equal to 1, the outward unit vector is negative direction of z, that is minus k cap. The total flux of f across D is given by the surface integral, that is equal to double integral over D f dot ds, that is equal to double integral over D x I y j plus z square multiplied by z square k dot minus k ds, that is equal to minus of double integral over d z to the power 4 ds only, that is equal to integral over d ds only, since z is equal to 1 and its value is equal to 9 pi. This double integral over ds represents the area, since integrand is 1 and area of the circle of radius 3 is here 9 pi. I will explain another example of the surface integral as follows. Evaluate the double integral over the surface S y z I plus z x j plus x y k dot ds, where S is the surface of the sphere x square plus y square plus z square is equal to a in the first octant only. Here phi is equal to x square plus y square plus z square is equal to a square. The vector normal to the surface can be obtained by finding gradient of the phi. The surface phi is given by x square plus y square plus z square minus a square. Its gradient becomes I del phi over del x plus j del phi over del y plus k del phi over del z. The value of this integral becomes, this gradient becomes 2 x I plus 2 y j plus 2 z k, and n cap becomes grade phi upon grade phi modulus, that is equal to x I plus y j plus z k upon under root x square plus y square plus z square, but x square plus y square plus z square is equal to a square. Therefore, it becomes n cap is equal to x I plus y j plus z k upon a, and here f is y z I plus z x j plus x y k. Therefore, the integral becomes f dot n ds is equal to double integral over the surface S f dot n cap dx dy over k dot n cap, that is equal to integral from 0 to a integral from 0 to root a square minus x square 3 x y z dx dy upon a z by 2, that is on simplification implies the integral over the surface S of the function f towards n dot ds becomes 3 integral 0 to a x multiplied by a square minus x square dx. So, on simplification it becomes 3 a 4 upon 8. Now, I will explain the volume integral of the vector function. The volume integral, let f be a vector point function defined on the volume V enclosed by a closed surface S. The volume integral is triple integral over the V f dV. I will explain the example to evaluate the volume integral. Here let us suppose f is equal to 2 z I minus x j plus y k. Evaluate the triple integral over the volume V of this integral this function f, where V is the region bounded by the surfaces given by x is equal to 0, y is equal to 0, x is equal to 2, y is equal to 4, z is equal to x square and z is equal to 2. The solution of the problem is as follows. The triple integral over V f dot dV becomes triple integral of 2 z I minus x j plus y k, and it is integrated with respect to x, y and z respectively. Then its limit becomes integral 0 to 2 for dx, integral 0 to 4 for dy, integral from x square to 2 for dz, and on simplification this integral becomes 32 upon 15 3 I plus 5 k, that is a vector constant. Hello student, today in this program I have explained some of the vector integration. I have explained the line integration of the vector function. I have also explained the conservative field, the integration of the conservative field. Here I have explained the surface integration with example. I have given various examples which shows the surface integration of the vector function. At last I have explained the volume integration of vector function also with an example. I hope you have enjoyed the lecture. Thank you.